Hello and welcome to tutorial 7 of Let's Learn C for Beginners. In this video I will be showing you how you can create text files and save them and then load them in again. I will also give you a useful object to work with text files, my string list manager, and then I will show you how to create binary files and open and save those. This should set you up nicely for whatever you may wish to do with files going forward, hopefully. And I will also present another manager called DataList to work with binary files, although you'll probably want to create your own sort of manager. This is just this one will just be like a template you can use for your own, I guess. So let's get into it. So first off, we will cover our string list, or rather my string list object and its useful functions. So this is obviously totally cross-platform here. So this is the program in Linux, but I also have it on Windows as well to so if I bring that across here, I'll go over some stuff in Windows first. So one thing to note is, because this is cross-platform, when we are working with files, we will be obviously referring to file system paths, and these are different for Linux and Windows. So Linux and Mac, pretty much the file paths are very similar, whereas on Windows the file paths, the slashes are a different way around. So I've split up lots of useful functions into their own manager modules and headers here. So we have the file manager here, and this has a function for getting our file name from the path, and then we have another function to just get the file path, and it backs up the file path. If you if I show you an example in Windows here, you'll see when I click on here, this shows you the different slashes here separating the various folder structures here. So if we wished to go to the next folder up using this string of text here, we literally would start at this end, the end here, and then we would go forward until we found this slash character, and then we know that we've essentially gone up in the path structure. And that's essentially what this this function here does. And also to note in here, where is it? No, it's in the main function here first, actually. In fact, no, it's in here, sorry. So this preprocessor argument here This will tell us whether the program is running on Windows or not. So what this allows me to do here is, if the program is being built on Windows, then it will create this boolean here, and it will set it to true, whereas if this is running on anything else, it will set it to false. And what this allows me to do is, and it will also allow you to do going forward, is when it is working with the path structures, if it's on Windows, then it needs two backslash characters like that to indicate a path separation, whereas everything else it uses a forward slash. So like Mac and Linux, they use forward slashes in their file paths, whereas Windows uses a backslash. But to indicate the backslash character, you obviously need two of them in the printf statements. So there's no operating system specific functions being called here. This is all native C handling here. So saving the text file. Essentially, you need the stdio header here when you're working with files. So I'll be better off sort of showing you this in Linux now. So all of the things I go over today, I recommend making sure that you have this site here bookmarked, and then any more details that you need to know you can find out by checking out the functions which I include in my various helpers. So for example, when we use stdio, the file type here is how we interact with both binary files and text files. And when we use files, we always use the fopen function. And then when you are finished with a file, you have to close it using fclose, and then you pass in the pointer of the file, because you'll see that the file is always a pointer here. So first off, I will go over I'll come back to Linux here. I'll pause this a moment. So let's go over the string list function. So the string list basically builds upon the C string object that I've been using in the previous tutorials, and this also I also will expect you to have watched the video on memory management and variable arguments as well, which will help you to understand what's actually going on inside the string list here. So basically what this is going to do is it will make reading and writing text files a lot easier. You can basically think of the string list as like the layout of like a page, where you have each line be like a single sort of C string, if you like. And then if you imagine these all ordered in a line, like going down a page, then that sort of helps. And you see that there's very few functions here. When we start off a new C string list, we have a default size, so I'll start it off with 8, and then every time it needs to resize after you've added a new C string or some chars, then it will grow in steps of 16. Obviously these are 16 C strings, and then we have a count indicator here which just says how many we have, and the capacity is obviously the total amount that can be held before the C string list needs to resize again. And just like most things which use dynamic memory allocation here, always make sure that you call the destroy function once you're done, as this uses calloc, malloc and realloc to change the size of things. I'm not going to go over the individual things here, just have a look at the functions to gain the use that you would have for this. It basically allows you to quickly sort of add C strings as you go to it, and then you can just sort of delete it when you're done. This ties in with the file manager functions here. So for example, the load and saving of text files, I literally just pass a C string list. So when you're saving a text file, the C string list should contain all the lines of text that you wish to save. And then when you're loading a text file, you would pass an empty C string list, and then all of the text from the text file would be passed into the C string list and then returned to you, hopefully correctly formatted as per the way you saved it. So I will now jump into using text files. So first off, it's going to help to go over working with files. So if we come back to here, the C++ reference site, and then the fopen here. Where are we? Here we go. So this basically is the function for all the opening processes here. So you pass in the full path and file name of a file to open, and then you pass in there's like a mode parameter which you also pass as a string. And then if we come down here, it gives you a list of the standard ones here. So all these are pretty much for working with like text files here. So this one here is for read only, but it says the file must exist. And then if you've got the R+ here, which is like an extension of read, then this will allow you to use it to read and update. And then write will create an empty file for you here. And then write plus basically gives you, well, it just seems to be the same sort of options really. So most of the cases, if you just do read and write, then this will overwrite whatever was there previously, whereas if you have a plus here, then this will allow you to basically like add to the end of that file. And then when we come to work with binary files, so the difference here between text files and binary files is pretty much all the stuff you write when it comes to text files is going to be in the ASCII character range. So if I, in fact, we'll just go to here. I've already got it here. So one thing you'll notice here is all of the characters are essentially in the range of 0 to 127. Obviously anything below 32 will not be visible. So everything we sort of put in the text file will be an ASCII representation. So if you save numbers to the text file, then obviously you will have to use the various conversion functions in here, which are, where are they? Is it in here? Yes, here we go. So if you were going to write double, integer, long integer, etc., then you would need these to well, if you were going to sort of parse them separately. However, we'll be using printf to format all the parameters that we sort of pass here. But if you needed to do things, pass numbers to the text file outside of using the string commands, then these were obviously what you would use here. And another thing to note in the text file as well is some of these things here have additional commands here. So you can pass like these other sort of things across here. For example, the you see the null character here is actually 0. So in C that indicates the end of a text line. And then obviously there's a backspace bell. The tab symbol obviously is decimal 9. So all of these you can actually pass in a text file. Whereas if you are saving a binary file, then obviously there is no defined layout. It's just whatever numbers you sort of pass into it. The difference, I suppose, is basically you decide what goes in your binary file. You have to decide the sort of host structure. So if you think of like whereas we have like header files here, you would have like you would need kind of like a header file to state what sort of format your file was going to be in, and you would need to remember that to be able to sort of load it in later. Otherwise the contents of your binary file would be unable to be deciphered. It'll make sense when you sort of play around with these things, as is always the case here. So let's go over our first example here. So first off, we are using the argc and the argv commands here, and the reason we are using these is because the first argument 0, is always the path of the executable which is running. And this is obviously useful for us so we can know where exactly our program is running on the host's file system. So when it comes to loading and saving files, we would expect our files to be in the local vicinity of the our program itself. So here we use the get file path function here, and you see this one here actually gets the file name from the path, and then we have this other global C string here for the actual path. So if I comment these out a moment here, and then we run this, so you see here this is the name of the file there, and this is the path. Now if I unpause the Windows one here, and I do exactly the same in here, so we will comment that one there out, and then I'll build and run that a moment. So you'll see here this is the our app name here, and then this is the location of our program on C drive. So the first example I will go over here will be making a text file here. So before we go into any details there, in fact I'll do that in Linux. I'll pause this again. These programs are basically totally the same, so I will I may as well just show you the rest of this in Linux to keep coming across here. So our first example here, we are using a number of simple functions here. So we will use input string here. So what this does is we basically pass a C string, ideally an empty C string, to this function here, and then what it will do is it will use scanf to read a string in from the command line. So this will basically allow us to freely type in a line of text, which will become useful in a moment. And then I have another one here for inputting a number here. So this one will take a number, an int, and then it will return that and read the value from the command line again. You basically send a message across here in the C string telling the user to input a number, and then there's the same here for using a float as well if you wish to do that. So let's jump into the MakeTextFile function here. So what this is going to do here, this will demonstrate using a C string list here. So the user needs to pass in a file name to this function, and then what it's going to do is we will keep reading strings from the command line using the input string function here until the user just inputs a single text character on a line, and then what it will do is it will save all of the strings which have been added to our text list C string here. As you'll see here, it will what we pass is the full file and path name to our save text file function, the C string list, and then whether we wish to append or not. And then we also have a little sort of error checking thing here to see whether it's saved or not. If it didn't save, then we'll print something out to the user to let them know. Regardless, we will destroy the temporary text list that's in here. So you'll see that this is just a temporary one that we use in this function here. So all it does is gets the user to input a load of lines, and then when you're finished, it will save a text file for you and then return true to indicate that's happened. So if let's make sure I've got that selected. There we go. Let's run that. So unfortunately, I can't scale the text in here. So anyway, so you can type in as much as you like here. And there you go, just type in a single character to end it there. And then it says the text list is about to be saved, and then press any key to end the program. Now if we navigate to the file path here, and then you'll see there's a text file saved here. So if you open that with a text editor, and you'll see here's our text formatted and output for us into a text file. Now the uses for a text file, you could have like an INI file if you've played numerous games. Depending on the complexity of the games, sometimes it's worthwhile to put in various settings that the player selects from whichever menus, or you can sort of create like a scripting file where you might have various parameters to generate internal processes in your program. So I will now jump into the file manager here. So let's go over the how the save text file works here. So first off, I'll just quickly explain some of these. There's nothing major going on here. Or what's happening with the get file name and the get file path is we basically find out how long the path string is, and then we start at the back of the path, the string, and then work our way to the left. So we would sort of start at T there, and then we would work back a char at a time, checking to see whether we found a slash or not, which is exactly what this is doing here. So we basically are recording we get the length of the string, and then we count backwards here until we either reach the start of the string or one of these slash combinations is found. We then break out here. We then create like a new string. So this one here is if we didn't find a slash at all, then obviously this is when we return the current path. Otherwise, what we do is we go forward one character here, because obviously we're currently at the slash character. And then what we do is we start copying chars from the path that we passed into our temporary C string chars, and then once we reach the length of the passed in file path, we then return the temporary string here. So this would literally just copy the name of the file, as you've seen. And then we do basically a very similar thing with the backup one here. Again, we start at the end, work our way backwards until we find a slash, and then instead of taking all of the characters to the right after the slash, we obviously take all the characters to the left, which would then return the backup of the path. So I will now go over the save text file bit here. So in conjunction with where are we? So here we are obviously working on just text files here, and then we'll be starting off with fopen. This is obviously the function prototype here, and then you see that if we've if we wish to append, then we pass in A+, otherwise we just pass in W. What that will do is if the file exists, then it will just overwrite it. Otherwise it will create a new file to save our text in. So if I come back in here, and then what we will do here is we will change that to true to append onto the end. Now if we run this again, what we should have now there we go, is we've added extra lines of text to the end here. So this is what appending does. It will just add stuff to the end here. Whereas if we didn't pass in append, then obviously it would overwrite the current contents of the file. So both of these will open our file for writing in different ways. One of the first things we must do once we've requested the file to be opened is to check that the pointer is valid. Obviously, if you pass in a weird name here with no file path on it at all, there's a chance that you might not be able to open that file. In the case of append, the file might not even exist, in which case a null pointer will obviously be returned as nothing has been opened. So you then need to make sure you don't try and write to that null pointer. So at this point here, if we've got a valid file, we now need to work with our list of strings here. So first thing we do is we find out how many strings are in the list to write, and then if the count is greater than 0, then you'll see we have a string pointer here that points to the first string in our list, and then we use a function called fprintf. So if I come back in here and we find that, you see here you can write formatted data to a stream. So all files are considered to be like byte streams, if you like. And then you see here the parameters expects is a file pointer, and then just like with standard printf, you pass in a const char array of letters, and then the var args at the end there if you if you have formatted characters in your text stream. So in this case, all we are doing is we are printing a string, and then we literally just take each C string's data and then put it in the fprint function, which then sends all of that to our text file. And then we just update the pointer there, and then we go forward to the end, making sure we write all of our strings into the text file there. And then at this point here, everything should all be good. So we make sure we close our file and then we return true. Obviously here, if it's a null pointer, then we say that save text file failed, and then we make sure we close this file anyway. So all avenues are basically covered here, and that's how you save a text file. And it's very similar in the opposite order. So now we've saved our text file. I don't have a function to load that in. It doesn't matter. You've obviously seen the actual text file, so there's no real need to load one in. So loading one in is just the exact same, but in reverse. Obviously, we will be loading one in a moment anyway, because I'll now go into I now have like a practical example here. So we will go over making a high score table, as this is obviously something that if you are creating a game you would obviously need. So here we have a list of names here for our players. So we have a function here to make a high score table. We have a struct template. Where is it? Here we go. So we have a high score item here. So you see we have a C string for the player's name, and then we have int for the score attained. And then here we have our high score table array. And then we have a simple function here which we can use to populate our array, the add high score. So you pass in a rank in here. This is where they are in the high score table. So this would be 0 to 9, as it would correspond to the table index. And then you pass in the player's name and the score they reached. And then we retrieve the high score item from our high score table, depending on the ranking you passed in. So really there should be a check to make sure that you're not going past the limit here, but I haven't put one in this time. And then we simply pass in the name to our C string here using the CStringNew function, and then we just copy our score value to the item's score here. And then this is our make high score table function here. So what we're going to do in here is we will create our list of high scores here. We will then create a file path. So you'll see here, this is the actual file name, and then we use our app path data here to get the location where we wish this file to be created, and then we use the save high scores function here, and then we pass across the file, the full file name here, which is what's happening here. You see we as I just said, we take the file path and then we add the file name on there. So in the save high scores here, we create a new text list, and then we basically go over each of the items in our high score table. We parse the details into a new C string here, so you see what we end up with. So I'll run that first. Let's come down here. So let's go in there. So you see here we've created the highscores.txt file there, and you'll see it's been created here. So if I open that, you'll see we have a number of scores here, and then we have a separator. So there is a useful C string function for working with separated characters. So if you go into string.h here, and then this one here string tokens is a useful way of splitting strings dependent on separator characters. So I haven't done an example using this, but in this case there's an example here. All it does is, you'll see there's a string here with all these different characters in, and then using the string token function here, you basically pass in a separate string indicating what the token characters are. You pass in a char pointer, or rather you have a char pointer to receive the starting string here, and then you use a while loop here while the starting character is not equal to null, and then this will basically split each string every time it finds one of these string token characters into a new line. As you can see here, this is the what the output of it is, where it split it to this a sample in string, because you'll see that there's a space character in here. So if you were reading like I don't know, like a comma separated like a spreadsheet or something, then this could be a useful way to do that. Anyway, so we've got our separator character in here, the comma. And this will bring me on to the load highscores function. So let's load our highscores and display them now. It's because I didn't pass in a name. So the load highscores here, this expects the full path and file name there. There you go. So that works now, as it's been able to find the file, and you'll see that we've separated the score here, and we've also added in the index in our table here. So to load our text file, so here we are opening our file using the R mode, which is just read. So if I split these side by side again, and then we have a look at fopen again. So you see that our file must exist to read, and then although I am not using these things here, I leave them here for you to see here. So there are some ways for you to find out how long a file is. So you kind of have to use this function called fseek. So if I come back up here, so the fseek function there's like an internal index in the file where reading or writing should be carried out. So fseek allows you to kind of there you go, reposition the stream indicator here. So you basically pass in the file that you've opened. So we have in file here. And then you pass in the start as a long int, which is why there's this L here. And then there are some the origin here. So you see there are some sort of predefined modes that you can sort of pass in here. And they are like seek set, or seek current, or seek end. And then you can use this function here, ftell, to basically retrieve whereabouts the stream indicator is currently. So what this will do is it will move the stream indicator to the end of the open file, and then we use ftell to basically tell us what that offset is, and that offset is in bytes. So once we have that, we know how long a file is, and obviously we need to know how long a file is because this will then allow us to use like calloc or malloc to create a buffer to be able to sort of copy the whole file across so we can work with that data. So once we've got the bytes, then you'll see we basically start back at the start of the file here, and then we are using the fgets function here to basically copy some chars across into our temporary buffer here. So if I open this one up, oh, not in there, sorry, in here. So what this will do is it will basically read a number of bytes or chars from a file and store it into a buffer. So in our case, what we're doing here is we are basically reading 128 bytes, or trying to read 128 bytes from the open text file and copy it into our buffer here. And then what we're doing then is we will add the new line character on here. No, this is adding a null character here. To the end of this string line here. And then if the length of this buffer is greater than 1, then we are adding this to our passed in CStringList here. And basically we'll continue taking chunks of 128 bytes here until the we run out of bytes basically. And then once we've copied everything out here, we then close the file and return true. Probably could have used fprint really to sort of get all this but this works fine anyway. So if you know that you're going to be working with text files which have strings inside longer than 128 bytes, then you might want to increase the size of this temporary buffer in here. So normally what I do is I have these functions here to load and save text files, and I basically forget all about how it actually works, which then allows me to proceed with other things. So most of the time you kind of get an understanding of how to open a file and save a file, and then you basically create functions to do that for you, and then you kind of forget almost of the internals here. So that's basically working with text files there. So like I said, we probably could have used fprint to in fact no, we couldn't have used this because this is saving to, I wonder if there's an fscanf. No, it doesn't matter anyway. It doesn't matter. I bet there is, yeah. Okay, but maybe we could have used that one. So this one could maybe have been an option instead. I don't know, just throwing that out there. So anyway, these are the save and load text files here. So the easiest way here is to just copy everything to our string list here. So all we've done here, once we've, if our load was successful here, then we basically we need to retrieve the data from our string to pass back to our add highscore. So this is where the sscanf function comes in useful here. So there are various file formats out there which use ASCII files for their data. So as an example, I don't know if you've looked at any of my other videos on loading 3D in on any of the consoles yet. But anyway, if you save anything as an OBJ file, so for example here we have an OBJ file here. So the OBJ wavefront format is, there is like an ASCII format which allows you to be able to read these things in text files. So this is basically the 3D parameters here, which creates a 3D cube here. So using the data in here, you can basically recreate that 3D model. Now the way to extract all of this is you'll see that some lines have a V, some have a VT, some have a VN, and these are common indicators in this file format here. The V basically says that this is a vertex, which is like a 3D point. VT is a texture coordinate, which is how you position a texture over a 3D model, where it kind of maps to. And then you have VN, which is a vertex normal. This is the vector that a light will reflect off a 3D surface. And then these F parameters here, these numbers basically say take one vertex, take one texture coordinate, and take one normal. And then using those three here, it basically takes one of these here, the index here. Anyway, the way that you would sort of split those up, if you were reading it, is you would use the scanf function to split one of those lines. So what the scanf function does here, so you see here it reads formatted data from a string. So this is basically, this allows us to take like a whole string line, and then we basically say what the string line should be composed of. And then where you see here, this %d is obviously a number, and then we pass an integer here, and then what scanf does is the reverse of what printf does. So rather than read the contents of this variable into the string of text, scanf is taking that number out of that string, converting it for us and putting it into the variable here. So the number from our high scores table here, side by side these. So you see we have %d and then we have a comma. That comma is what we ignore, but is in here to allow the scanf to basically know where the different parts are of the string. And then this parameter here basically allows us to take a string with various symbols in it up until it gets to the new line indicator in the text, which is obviously a hidden character in here. And then what it does is it copies this string into the player name data C string here. You'll see that there's item there, there's player name, and there's score. So these are temporary variables to hold score and player name from our high score line of text, which it's reading from the text list that we've loaded our text into. So here it's basically going through each line. So it's going line by line here because this has all been copied into the text list. And then once it takes the score and the player's name, you'll see it uses the add high score and passes them back in until it gets to the last line of the text file here. As you'll see, once it's loaded, the number of lines is copied into name count, and then there's basically a do while list here, loop here, sorry, which basically adds all the data back into our highscore table. So using, if I open that back up again a minute, is it going to find it? Yes, it is. Okay, open it then. It must be because so if I come back to here a minute here, so if we wanted to read this line here, say it was in a text file here, so the first one we would have V, so we would skip over that, and then there's a space, and then we would have %F space %F %F, and then we would have our three floats like that, and then that would take that number there, put it in a float 1, take that one there, put it in float 2, and then take that one there and put it in float 3. So using scanf is a good way to format your lines of text. Once you create like a text file with however many sort of parameters for one line of data, so you don't have to sort of save it as .txt. You could save it with any sort of file ending you like, which would obviously confuse the operating system that you're on, but then that's not important. What's important is you know what's in that file, and you know that you can read it as a text file. So if you didn't save it as .txt and saved it as .bin or .dat or whatever, then that just means that most people wouldn't be looking in that file, because the operating system wouldn't default to opening it with a text editor. So you could save whatever into a text file, write numbers, text, whatever, and then use scanf when you reload in that file to reformat out the parameters. So I just thought I would add that in there for you. So that's the loading part here. So I've already covered the text load file here, so that's pretty much it for our text file stuff. It always helps to give a real world example, I feel, with lots of coding. It's just so that you can get an understanding of the point of it. Which is why I've also split the file manager stuff into its own sort of header and module. So some of these things you can literally repurpose for yourself outside of this example here. So the next files we need to talk about are the binary files. So the thing with binary files is you need to decide what you put in them. It's obviously, it can be anything, but obviously to anyone outside of that file, unless you give them the key to be able to reopen that file, then they potentially won't know how to read your file. So when it comes to binary files, you can think of it as like a list of, well, it's basically a stream of bytes. Whereas with the text files, everything is kind of formatted to chars, where everything would be within the range of 0 to 127. When it comes to binary files, each byte may be a byte on its own, or it could be part of a short, or it could be part of a long, or it could be part of a float or an int. As these data types can basically be all packed in together. So if I come back to the highscore thing here, so you could easily have put these into a binary file, except as you were passing these into a binary file, an int obviously takes up 4 bytes, and your string would obviously be however long that was, but it would still be readable text. So when it comes to working with binary files, for example, you need to sort of create like a header structure of how your file would be laid out. So for example, say you were saving level maps or something like that. So you would have like a, maybe you would have like a map width, map height, and then you might have your map so it would probably be something like that. So in fact, let's so to be able to sort of have this, what you would how you would sort of format this is, this would be 4 bytes, this would be 4 bytes, and then this would be basically an array of bytes, which would basically be map times map width times map height. And then if you had a number of levels stored in that file, then when you sort of saved it, it would obviously save it as like a string of bytes, and then to read it back, only you would know what was actually in that file, and then you would have to extract 4 bytes for a width, 4 bytes for a height, and then the next load of data in that file would all be of 1 byte each times the map size. So that, hopefully that might make some sense to you there. But anyway, we'll go into the next part now, which is the data list object here. This might also help clear some things up, what I was saying just now. So the data list type here is basically a generic data list, as in, although it's a stream of unsigned bytes, basically, you can add in any data type you like to it. So internally it's got byte size, which basically indicates how many bytes are in it. So if you add 1 byte, then obviously you add 1 to byte size. If you add a word, which is basically a short, then 2 bytes will be added. If you add an int or an unsigned 32-bit number, a D word, then that's 4 bytes added here. If you add a 64-bit number, a Q word, then that's 8 bytes added here. No, sorry, that's 16 bytes. The U32 is the U32 is 4, and the U64 is 8. No, that's wrong. Sorry. The word is 4 bytes. The 32-bit number is 8 bytes, and the 64-bit number is 16 bytes. Sorry about that. So essentially, the correct number of bytes needs to be updated for each data type you add to this data list stream. And to be able to read those back, you obviously need to know in which order to retrieve these data types, as they all take a varying number of bytes to copy back from the data stream. So this basically allows you to mix and match data types. I could have added in a float here as well, but I didn't, to keep this more simple. So as a note, the string list, I obviously use that myself for various things. This here I have never used. I don't generally create binary files myself, although I could do. I haven't as of yet. If I did, this would probably be a decent structure to actually use to manage them. Although you might want to maybe just restrict your reading and writing to maybe just one data size. So if you were to, let's try and think of any sort of file. Let's think. So if let's ask AI. So here we go, as an example here. So a BMP file, a bitmap file, is basically a binary file. So to be able to read back that binary file, you need to know the structure of a file here. So you'll see there's a file header which takes 14 bytes and also contains the letters BM. There's then this device independent bitmap header, which is 40 bytes usually. And then there could be a color palette, so you would have to check somewhere in the bitmap header to know whether there was a color palette. And then after that there will be the pixel data, which is basically stored and aligned to 4 byte boundaries. As potentially if you were reading a 32-bit image, then you would be, when it comes to the pixel data, it would be unsigned ints, 32s you'd be taken back. So you would obviously read in, if you were to sort of write that out, you probably might not be using this sort of thing here. You'd probably need a struct to actually handle that. and then you would obviously create an array big enough to hold that bitmap if you were loading it back in, and then you would probably cast the data stream to a struct layout. So for example, you might have something like and then you could have the sort of like so you could have something like this. And then you would kind of, this would kind of indicate how you were going to be reading and writing stuff across into your binary sort of format. So I'll quickly go over some of this here. So the new function obviously creates the default size for it. So I'll set that as 1K there, and then it grows in half K steps, or half a kilobyte steps, which is 512 bytes. So with all of these things here, make sure that you let's rearrange that a moment. Always make sure that you call destroy on these when you're finished with them, because obviously they are allocating things from system memory. Otherwise you'll be causing memory leaks. So resize basically allows you to alter the size of it to a set amount, and then using set size 0 you can set the byte size back to 0 again. So this is here just in case you wanted to resize this to be able to fit something new onto the end of your existing data. And then the add other here, what this will do is it will basically copy the contents of another data list into your current data list. And then these just allow you to sort of add bytes, words, D words, Q words here. So all what's happening here is if we add a byte for example here. So we're always checking to see whether the array is null or its capacity is 0, which would indicate that it's actually empty. If it's not, then we first check to make sure that if we add 1 to the byte size, that it doesn't exceed the capacity that's currently in place for it. If it does, then we obviously need to reallocate. So grow the current data stream by the grow size here. And then after that we add our new byte to the end here. Now if we work with a word or a 16-bit number here, then we check whether it's byte size plus 2, because obviously it takes 2 bytes. And then if we are obviously working with int, it's 4 bytes. Yeah, I got that wrong just now. It is 4 bytes, and it is obviously 8 bytes if we are working with a 64-bit number. and then the get byte function. So all of the get functions here will rely on you knowing at what byte index that data type actually should be located, which is where a kind of like a header or some sort of layout record that you created would need to be in place. And then to get the other types, or what happens is it basically creates a cast here at the specific index that you passed in to return that data type here. So you can basically cast the byte stream array at a certain position into the new data type that you wish to retrieve. And then it obviously happens in reverse here. So if you're adding a keyword here, then in the keywords case, we get the byte size indicator, or the position. So when you add something, the index, as in the byte size itself, is automatically updated. But to retrieve that number back, you need to know where in that byte stream that data type is actually located, which obviously could become complicated if you don't record this. And in this case, it's using memcopy to copy the value you passed in into the respective place in the data stream here. Whereas if you look at the add word one here, what we're doing first is we are casting the byte location to a 32-bit pointer here, and then we are assigning our value we passed in into the data list here, and then we update the byte size by 4. A bit more complicated, this one. Hopefully it makes sense to you if you decide to use it. So let's go over using it now. So let's come down here. So what we're doing now is we are making a data file, and then we pass in a name for it here. So if I come up to that, so we create a new data list, and then you see here we have a faux file name CString in here. And then what I'm doing here is I have a byte here, I have a word here, a D word here, and a Q word here. And I'm basically generating a random number in the range that data type can handle. So for example, max byte here, you'll see this is going to be a number between 0 and 255 there. And then there are some predefined data types here. So in the int types header here, this is needed for Windows to be able to print out 64-bit numbers in printf. Where is it? It's in standard int here. So in this header file here, not only does it have these data types it also has the minimum and maximum ranges. So you'll see int n max, you replace that with 8, 16, 32 or 64, and then that will tell you the upper range that that data type can hold, basically the maximum number or the minimum number. However, we're kind of limited to the rand function here, as if we look back in here, so I think that's in standard lib. So you'll see the rand function is obviously limited to an integer, which obviously is half of a unsigned 32-bit number. So it can basically contain a random number between 0 and 65535. So for us to be able to get a 32-bit number, where are we? Keeps resizing the stuff here. There we go. So for our 32-bit number, we basically add two random numbers together, and then for our 64-bit, we basically add 4 of these together, and then we use the max word range here. And then one important thing to note here, so in fact this is where the sort of confusion comes in, because so to display, obviously it takes 4 bytes, but obviously to display them, it obviously takes double that in a text file. That's where my sort of confusion was coming in here. So to display the maximum D word range here in hexadecimal, you can do that fine on Windows, Mac and Linux. However, if you try and print out a 64-bit number in printf on Windows, then you have to do it a different way than Linux and Mac, which can use the LX or LLX parameters inside a printf statement. So this can be used on Linux as well, I believe. But you see that you have to do percentage and then quotation PRIX, and then you either have like a D, a U, lowercase x, or whatever the normal sort of character would be in the printf statement. And then this allows you, this then is replaced with your 64-bit number at the end here. So all this is doing here, we generate some random numbers to put into our data list. We then print out what they are. And the reason why is because once you save this file, the only way you can sort of view it externally would be in some sort of hex editor or some sort of file browser, I guess, if it allowed you to read the raw bytes of any given file. So here we basically add our byte, word, D word and Q word to our data list, and then we pass that to the save data file. So let's jump in here. So it's basically the same as what you do with the text file. The only difference is when you work with binary files, you have to add a B after the append or write part. And then all we do here is we use the fwrite function. And basically all it does is it basically streams an array of bytes into the newly created file. There we go, write a block of data to a stream. And then this is what it expects. So this is your array of data here, which it converts to a void pointer. You then say how big each element of the data is. So you could save a load of structs this way. So this could be an array of structs. This would be how big one of those structs is in bytes. And then this is how many are in this void array here. So in our case here, it's right in bytes. So each element size is 1. And then we are writing the amount of bytes in our stream to our file here. And then this will return how many bytes has been written to the file. So you can then use that to compare against the size of the data in your file. And if they don't match, then there's an error somewhere, as it hasn't written the full file to the whatever medium for some reason. And then if that's the case here, then we output an error here. Maybe there's not enough room on the location on the user's hard drive or CD or whatever. So you'll see here, if there's a mismatch in byte size and the length of bytes written, we generate an error, close the file, return false. If for whatever reason the file path name and whatever was invalid, then after the fopen command here, this would be a null pointer. We obviously need to catch that error as well, which is what's caught in this block here. And obviously we say the error couldn't create the file. And then if we've got to here, then everything's fine. Close the file as per normal. And then we return true. So that's how you save a binary file. So let's do it. So this will make our binary file here and save it. So let's do that now. So here we go. So these numbers are all in hexadecimal, by the way. So one thing to note here as well is the order of bytes written. So there are little Indian and big Indian byte formats. It depends on the CPU that your program is running on. So if you were doing this on like an ARM chip or an ARM based system, then when you come to write in words and anything bigger, these bytes would be reversed around the other way round. So 9A, 9E would be represented in bytes as, in fact, it's reversed them here anyway. So on an ARM system, it would put it as expected, so it'd be 9A, 9E. It would be written as you see it here, but on the desktop, that's the opposite way round, where it's low byte, high byte format. And then you can kind of see the same thing happening here. So it goes from the lowest byte to the highest byte in order there. So it's CF67 and then 01 here. So for us to actually double check this here, what we need to do is, so here's our file here that's been created. The MyData.binary here. So to open this, the operating system will have no idea what this actually is. So in my case on Linux here, I have a hex editor. So now what we can do is we can compare byte streams against each other. So you'll see here we have 40, 9E, 9A. So these match basically. That's what's in that file there. So this is a quick way that you can check contents here. I don't know if you can actually update data in here or not. So this is how you would kind of alter files or inspect them, any files. So that's our binary file written there. And then to load that back in, so we already know the format that's in. However, I should have opened that again a moment. Let's open that again because we'll need this to verify the bytes here. So there we go, there's our byte stream here. So now we want to load in this here and display the list of bytes. So our data file is loaded here and it's listed what's in that file. So if we open this one back up again, you can see that it's got everything we wanted inside of it. Fine. So let's have a look in here now. So here's our data list here. And then obviously we create a file name for it here. And then we are literally just passing in our data list here to the load data file function here. So this one's a bit more complicated now because what we need to do is we need to load everything in. We also need to get the length of it. So rather than loading each byte at a time here, what I'm actually doing is I'm just getting it all in one go. So you'll see we have another data list inside here, and this is going to be the temporary medium to copy the whole capacity of a file into it. So at the start here we we obviously read it with RB to read a binary file. And then using fseek and ftel, we find out how large the file is, and then we use rewind instead of the other sort of fseek command that we could have used. This basically does the same thing. It basically sets the stream indicator back to the start of the file again. Then what we do is we use the file length to create our data list with the same size as it. Obviously, if there's an error here, then we destroy the temporary list here, return false. If not, then what we do is we use the fread command. And this does exactly the same basically as fwrite, except in reverse. So what we're doing now is we pass in the destination for the byte stream from the file. We then pass in the size of one element and then how many of them there are. So you'll see here we're basically doing the reverse here. So each element is 1. We then pass in the file length, which we got from ftel. And then what this will do is this will copy all of the bytes from that file into fread. No, sorry, this will copy it into the byte array inside the data list structure. And it will return in read count how many bytes it's copied back. We then make sure that read count and file length match. If not, there's an error. And then what we do is we then need to set the byte size in the temporary list to the same as the file length and the file capacity. Because we've loaded in this data here, obviously the byte size indicator inside of it has not been changed, so we change that now. And now what we can do is we can use the datalist add other function to copy the temporary lists data into our passed in data list here for retrieval by us. Then if that worked, we can destroy the temporary list here and return true. Wait there a minute, did I close the file? No, I did not. Okay, I must have missed that yesterday when I typed that out. Let's put all those in there to make sure we make sure I'm not passing you something that's going to cause a memory leak. That's right, it's closed in there. Okay, so yeah, that passes it all back to us there. So binary files are obviously more complicated. You need to know the exact layout of things inside of it. So one way is, as I've showed you here, is to just pass it as like a byte stream. Another way could be to save things as maybe a linked list of structs or something like that. Again, it's entirely dependent on the task that you have at hand. Anyway, that kind of sums everything up for this video. Hopefully it's been useful, and some of these data types here you can find use of in your own programs going forward. So that's it for this video. Let me know if you have any questions in the comments below. And in the next video, I will cover using libraries. So static libraries and dynamic libraries. So thanks for watching, and I will catch you in the next one. Bye for now.